开始连接话筒。已解锁，请取出话筒。
Okay, I have uploaded all the lecture notes already. You can check up to point correct duality. So, sorry. Yeah. So I guess the total is around 1,300 slides. So we are at the how many slides now? We're at around 700. So that's another half. Okay, but for this half, right, we won't plan to cover everything in details, but we will mention all the main points and focus on some calculation. That's all. I'll let you know what will appear in the final. Basically, for homology, you will repeat everything in homology. So that's part of it. For anything you can see in homology, you will see in cohomology with an arrow change, but later we'll tell you what's the arrow change. And then we, on top of the thing that we can do for homology, we can do something called a cut product. We can take product of homology together. So we call it homology. And so we can take products, cut products, and then we can take cat products. Yeah, those there are two kinds of products. Okay, so the cut products will tell us the algebra structure, and then cat product can tell us the duality, the isomorphism. Basically, point correct duality is isomorphism between two vector spaces or two modules. Okay. So you should expect that if these modules are finite generated, the duality, the isomorphism you see should be just matrix multiplication. Okay. Yeah, but we will soon go there. Hopefully today we can finish Mayer-Vietoris sequence, and then we can wrap up for homology. Okay, but before that, so I need you to read because we don't have quiz anymore. Please read before coming to class, and then can straight away ask me a question if I miss any main point. You can ask on the spot, so that I can either tell you or I can figure out after the class. So before we continue, right, last lecture we stopped at Euler characteristic. So we computed the cellular chain complex for orientable genus G surface and also non-orientable, right? Okay, so they are like 1 0 cell, 2G of 1 cell, and then 1 2 cell. Still remember? For orientable case, we glue along the commutator. Okay, so in this case here, we have this characteristic, sorry, the Euler characteristic 2 minus 2G, because 2 coming from the, so 2 split to 1 plus 1. So 1 is 0 cell, 1 is 2 cell, and then their power is minus 1 to the even, so it's plus 1. And then 2G is the number of 1 cell. So 1 cell is odd power minus 1 to the 1. So you have minus 2G, 2 minus 2G. Okay, so this is the Euler characteristic. And then for orientable surface, for non-orientable one, we only have, do you still remember last time we computed homology that is Z to the G minus 1 plus Z2, okay, plus Z2. For Z2, right, it's not counted as rank anymore. Okay, for rank, right, we just count for the Z subnet. So Z2, those term is like a portion. Okay, we call it portion. Okay, for those that have a finite order, yes, good. Finite order. Okay, we call it portion. It's not counted as rank. For rank, we need the infinite. Okay, so there's only ZG minus 1, G minus 1 of them. And then plus 1, where is the 1 come from? Okay, yeah, miss out anyone? No, okay. So, wait, so what do we compute for the cellular complex last time? Also forgot. Yeah. Yeah, this one, H1. H1 is ZG minus 1, And then there's no H2, is it? Yeah, H2 is 0. Okay, so there's no contribution for H2. So there's 0. So the extra 1 is coming from the connected part, which is H0. Okay, so that's why you have this. Yeah, so that's why you have 2 minus G. Okay, so you can see that the Euler characteristic here is characterized by the number of genus you have. Okay, number of genus. Okay, how many holes in particular inside your surface. Okay, or not? So if you notice the G, let's look at the orientable case. G0 means what? Is a sphere. Alright. So G0, that the orientable characteristic is 2. 2 is greater than 0. Okay, 2 is greater than 0. And then if you go to G equals to 1, okay, G equals to 1, it becomes 0. And then G equals to 2, it becomes negative 2. Okay, so you can see that this genus, right, with different Euler characteristics, actually they are different geometry. Okay, so basically this world, right, the geometry is split into three types. Okay, if this Euler characteristic is greater than 0, then you are a spherical geometry. So you get a spherical geometry. If it is 0, then you get a Euclidean geometry. Okay, it's flat. Okay, and if you get less than 0, then it is a hyperbolic geometry. So how do you see this geometry differently? You just look at triangle. Okay, so from primary school, right, you know that triangle, the internal angle add up to 180. But this is not the case for spherical and hyperbolic geometry. So if it is spherical, then your triangle, the internal angle should add up more than 180. If it is hyperbolic, then it is less than 180. So maybe there are 3 pictures maybe you want to see here. So one of them is like this. Okay, and then the other one is like this. Wait, there is 0. Because 0. Okay. Okay, so this is the spherical. Yeah. You begin. Then this is okay. This is something you can learn in a differential geometry. Okay, so differential geometry also characterize this as a curvature. Okay, so the relation between curvature and Euler characteristic is a very deep thing. Okay, so there's a relation between curvature and Euler characteristic. Sorry, Euler characteristic. So this is a Gauss-Bonnet formula, very famous one. I think so. You can learn it in differential geometry, I guess. I'm not sure. You can ask Arash to teach this or not. Gauss-Bonnet. Yeah. So this is I haven't finished writing everything here, but approximately, okay. There's something you need to fill in. You need to integrate over one. Then I think there's a 2 pi around here, if I'm not wrong. But this formula is what makes Chen famous. Chen give a very intrinsic proof of this. That's why the whole Chinese community is like working on geometry analysis in the last century. This century, I think they also shift to algebraic category theory because a lot of Chinese they went up to US to study, and then they went back to China working again. Okay, but this is yeah, but this is still a main trend in China, which is called the geometric analysis. 还有一下什么东西？落在哪里？
还有一个小配基底的，
配基底，
它也叫 geodesic curvature.
Yeah, there's a lot of few curvature. I think this is a total curvature, if I'm not wrong. There are 3 types of curvature, but yeah. Yeah, there's a lot of curvature. Yeah. Okay, I think you will learn those in differential geometry if you take it. Okay, right. Okay, and then you should recognize this 2 minus 2g from somewhere else actually. This is some other number that we met in algebraic geometry. It's canonical devices. Okay, so canonical devices actually have something to do with the solenoid calculus. This canonical device is defined on the smooth projective curve with genus G. Yeah, doesn't matter. Doesn't matter for now, but I just want to tell you that algebraic geometry can tell something on topology. Okay?
最魔幻的 chapter。
Yeah. Okay. Yeah. Okay. So let's continue then. Yeah.
我才要用到。
我不知道，有用到吗 ？Is it？看一下哦，我赶去 check 一下。可能如果我慢教的话就可以用吧。如果是可以蒸出来就要蒸哦。如果是看 lecture，哦 lecture，看你讲先，如果晒它也是可以。看了我还不知道我讲解了。
Mayer-Vietoris 你有讲吗？
我要讲啊，现在不可能用到吧？上个3没有用到咩？Mayer-Vietoris 没有吧？上个3应该没有用到 Mayer-Vietoris 吧？这么冷气好像有点热。Okay, right. Okay, let's continue. So we want to finish Mayer-Vietoris today. Okay. So Mayer-Vietoris, okay, good. So let's say we have retraction. From X to A, okay, such that it will compose with the inclusion to get identity. Okay. Then we will see that I star is injective. Okay, because the induced map is R star I star equals to identity star, which is identity. Okay, so what this means is if you look at the long exact sequence of the pair XA, then the boundary map is actually 0. Okay, why is it 0? Because I star is injective, right? But this long exact sequence is exact, meaning what? The connecting homomorphism has image 0. Meaning what? What's the map has image 0? 0 map. Okay. So this means that we can split the long exact sequence into a few short exact sequence like this. Okay, because the boundary map is 0. Okay, so now is so we can ask what's the relation of this? Okay, what's the relation of this? Okay, so what's the relation between these three things? So the lemma is, this is called the splitting lemma. So the splitting lemma is if you have a short exact sequence, if you have some way to go backward, for example, C to B, let's say this is X, or you can go from B to A, J, okay? Then this B here will be isomorphic to A plus B. That's right, A plus C. Okay. So actually, this is a desired thing to do. Okay, this is a desired thing to do. What do I mean by that? So what I meant is Because if you look at the exact sequence, right, the kernel of P is I. Okay, kernel of P is I. So meaning what? Everything that gets sent from A to B should get sent to 0 by P. Okay. So this constitutes part of B that sends to 0 in C. But this P is surjective. So meaning what? Everything in C should be able to write in terms of P. So the thing that written down here is we can just build everything of B by using A plus C. That's all. There's nothing else already. Make sense or not? Okay. So, but to do this, we need to have this map going backward. Okay. Either number 1 or either number 2. Okay. One of these exists is enough already. But it turns out that if you have one of them, these three are actually equivalent. Okay, you have a splitting map of X from C to B, automatically you can build one from B to A. Okay, so let's say you have this S or J. Can you build the isomorphism or not? Okay, can you build the isomorphism or not? Okay, so actually, what's this isomorphism is? So let's take A and C. What you do is, what's the obvious thing you can do? Let's say you have an S. Okay, the obvious thing you can do is you can apply I to A and then plus S to C. S to power C. Okay, so the thing you need to do is to check this map is injective and then surjective. Okay. Homomorphism, I think is easy because I and J is already orthogonal. Okay, another thing is another condition for A direct sum C is you need to check that their intersection is 0. Okay, that's another thing you want to check. Okay, so far any question? No. No. Okay, so this check is actually very straightforward. It's very straightforward. You can have a look. So the main thing here is if you want to write down this direction, you must have a splitting map. Okay. So this is what the proof I provide you in the lemma last time to show that our reduced homology, no, the zero homology split into reduced homology plus the Z component. Okay, we produce the inverse map Z going back. Okay. Yeah. Otherwise, you can use this with splitting lemma. Yeah. Is it straightforward? Okay. Okay. If you don't have this inverse map, the thing doesn't always split. Okay, doesn't always split. Yeah, I got the examples here. So, for example, things that doesn't split. So SES that doesn't split. So for example, let's look at Z3 going to S3 and S3 going to Z2. Okay. So what's this map here? You send 1 to 1, 2, 3. Okay, 1, 2, 3 is order 3. So you send to order 3 element. And then you need to map into Z2, right? Meaning you want to send the order 2 element to the generator because you need to preserve the order. So for example, 1, 2, and 2, 3 can send to 1. Okay, then 1, 2, 3 will get sent to 0. Or not? Okay, so the claim is there is a splitting. Okay, so there is a splitting from see this. Do I have condition on this splitting lemma? Later I confuse you. Okay, so this splitting lemma only work for abelian group. This is abelian group. Okay, so very dangerous. I didn't tell you what is ABC, so you don't know how to construct a counterexample. So here, purposely pick a non-abelian thing here. Okay. Yeah. Sorry. Yeah, lemma is abelian. So I pick a example for non-abelian because abelian I already proved to you always work. So in this case here, it doesn't always work, although you have a splitting map from Z2 to S3. Although there's a map here, one going to 1, 2, but you cannot find a surjection from S3 back to Z3. So you cannot find this map here. This J we cannot find. Okay, such that J and I can square. Okay. Yeah. Okay, I think here important thing is homomorphism. I think you can try. Okay. Yeah. For abelian case, it works, right? One of them exists or the other counterpart, but if it is not abelian, then you might not be true. Any questions so far? Questions so far? Okay, to convince yourself, maybe you need to try and work it out. Suppose there is a surjective map. Using that, and then maybe I think it will contradict with the homomorphism. We can try it out. Okay, so far. Okay, so corollary here is, I think this is the main thing you want to remember. So if you have a retraction, okay, from R from X to A, then this will give a splitting of Hn(x) isomorphic to Hn(a) plus Hn(xa). Okay, if you have a retraction, you can write this. Okay. So retraction is the splitting for the inclusion map. Does it make sense? Okay, so we'll say that SES split if any of the condition in the splitting lemma. It's any condition splitting lemma. Okay. So far, so good. Okay, so let's try some one example actually. The other example I'll let you see also for mappings later. But we're gonna prove Brouwer fixed point theorem again. Oh, by the way, we got the project topic chosen, Adam's spectral sequence, and then homology of group, and then the Ram homology, and then Bosso-Ulam theorem, and then fundamental group and homology. Okay, so the rest you can try and choose other stuff. Oh, there's another interesting about homology is intersection homology. Okay, if you're interested, you can look around for intersection homology. Okay, these homology homology are really equivalent. So yes. Good. Homology are good. Yeah, I don't know. Yeah, we I can tell. Okay, so I think we proved Brouwer fixed point theorem twice already, right? So one of them we use the pi one. The other one, what did we use? Brouwer fixed point theorem. Degree is using degree. I remember we proved twice already Brouwer fixed point theorem. Lifting something also related to pi one, right? Okay, but now we're gonna use homology to see. So let's say if we have a retraction, okay, going from Dn to Sn minus 1, right? Then this will give a splitting of Hn minus 1 D isomorphic to Hn minus 1 Sn minus 1 plus Hn minus 1 of Dn Sn minus 1 because Sn minus 1 Dn and Sn minus 1 form a pairs, right? Is it possible? Is this possible? Is this splitting possible? What are these each term here? Well, this term is contractible, right? Dn, so this is 0. But this term, there's something happening. No, don't really know what about this term, but you cannot have z plus something equals 0. Okay, so this is impossible. Contradiction. Okay, so there's no retraction from Dn to Sn. Yeah, so there's a lot of way we let you see that Dn cannot just retract to the boundary. Okay. So one way, very easy, intuitive way to think about is if you're gonna do that, you will kind of like creating a hole inside your Dn. So, 我哋要拉開，貼你誒，貼你入去，得啦。Okay, so far, any question? Hey, there's a very good advancements news in mathematics research area now, which is called the Takeya conjecture. You can go and watch it. Takeya conjecture. So basically, it says it starts with a question that if you have a needle and then you move the needle around, okay, what's the minimal area that it can occupy? Right? What's the minimal area it can occupy? So, for example, well, I mean the easiest case is you fix the middle and then you turn it around, right? So you get a circle, okay? But there's another way is you can like move the needle around like repeatedly. Can you imagine what I drew? My animation is not good yet. So like, I think like this, you can see it. Okay, so you move it such a way that it intersects the area that you occupied before, such that you can form this kind of thing. This is a much smaller area than the circle, right? Can see a lot like this. So your needle is like go up and then go up. Right. Okay. So this is a much smaller area than the circle. Okay. So the question is, what's the smallest circle? What's the smallest area? Yeah. So it apparently is proven by one Chinese girl called Wang Hong, I think. Now she's a professor in IHES. So she's like, IHES is a research center in France. And then Gordon was there before. And then yeah, so she go around the world and then do the tour explaining her proof. You can watch. She is like very calm. Yeah, you can go on. Yeah, very calm. 她讲话很冷静，很好，去看一下，多看几次。Yeah. Okay. I think she solved it with her supervisor, I guess. And then her supervisor, I don't know colleague or supervisor. That colleague is in British Columbia. Okay. Yeah. And then this has, in fact, this has relation with harmonic analysis. 可以拿去问陶轩一下，懂这个东西。The question is, if you do Fourier transform, right, you transform your function into basis of trigger in different period, right? Let's say I give you all these trigger function, right? Can you recover your original function? Turns out there's a relation between this and that. It turns out that you cannot. Why cannot? Because of this Kaya needle problem. This provides a solution. Yeah. Okay. Larry? John Carlson. 叫什么 John Carlson? Okay. 因为他写的 paper 的另外一个人不是叫 Larry。Okay. Anyway, good. Good. I think we are good. So we continue with Mayer-Vietoris sequence. We are not attempt to prove these. I don't want to spend time to go into the technical detail. 没有 Van Campen 那么麻烦。没有 Van Campen， 比 Van Campen 容易。只有1、2、3、4面吧，比 Van Campen 容易。OK， 你可以看一看比 Van Campen 容易，没有。Okay, so what is Van Campen doing here? So this is a analog of Van Campen theorem. So you should think about what we need for Van Campen. So basically, we need to decompose our space into, let's say, AB, okay, U or UV, and then we need to talk about the I1 of the intersection include into this open set here. So similarly, we will do it for the Mayer-Vietoris sequence here. Okay, so you have X, okay, and then you split into interior of A and interior of B. So maybe this A can cover around here, right, and then B will cover around the other side like that. So this is B, and then this is A. Yep. Doesn't matter. So there's an intersection. Then what we can see is we have a long exact sequence. Maybe you want to remember this. I think this is the main thing you want to remember. So the first term is the intersection. Okay, we'll go into the direct sum of A and Hn of B. Only then you go into the large space. Okay, so you should think of how we get this. So this coming from direct sum. Okay, direct sum of AB. And then union, okay, in particular union. So union split into direct sum here. Usually union don't split into direct sum, only wedge sum split into direct sum. But in this case here, we have this long exact sequence condition. Okay? And then the connecting set that connect X to the intersection. Okay, so when do you think this idea is applicable? Only when you know what is the topology of intersection and you know the topology of the cover. Right or not? We like to relate everything back to Sn that we know how to compute. Or torus, at least we know how to compute. So if your intersection is just a circle or that things that you know, then you want to use this Mayer-Vietoris. Okay. For the open set, maybe it's contractible. Right. For example, if sphere, right? So you split into southern hemisphere and northern hemisphere, then what's the topology of it? Contractible. Then you will provide these two terms become 0. Then you can have a bunch of isomorphism appear. Does that make sense? Okay, so this is one way to decompose your space to some other space that you know about. Okay? The proof is quite delicate. You can have a look, but we don't want to dwell on it. So imagine so Van Campen, we also just proved to you for 2 cases, right? But actually in Hatcher, right, they put union of n open set. Still remember. And then thrice intersection is path connected. Okay, so there's a lot. So we can do this for Mayer-Vietoris sequence. But for those cases, right, you can't just have one long exact sequence. You could imagine there's a lot of intersection, a lot of direction appearing. So instead, we will need something called the Mayer-Vietoris spectral sequence. Last time I told you, right? Spectral sequence is like a texture of chain complexes. And so you need a spectral sequence to work it out. Okay. So for our case, we just focus on decompose your space into 2 open set. Okay. And obviously, there's a reduced version. Okay, so what do I mean by reduced version? So meaning you can augment it. Okay, you can augment your short exact sequence of chain complexes. Okay, with Z. Okay, you can augment this. So this one is the chain level. This is the homology level. Okay, if you look at the chain level, you can augment your SES of chain complexes with this Z to Z plus Z to Z. Okay. So actually, this long exact sequence, you should ask it come from which long as short exact sequence. of chain complexes. Okay, it comes from something that looks like the bottom bit. Okay. Yeah. Sorry. Why A and B are? What do you mean by path connected? So this is the augmentation. Yeah. It's like the reduced homology, right? You augment in Z. And after the C0 term. So there's two C0 terms here, right? And two Z here. And then this C0 A plus B is yeah, you augment another Z. Yep. Huh? Why C0 is always 什么？
是 augmentation。
Augmentation 一定是放 integer. There's a surjective map into Z. What's the surjective map here? Do you still remember? You sum up all the coefficient. 不一定，这个只是 augmentation 吧，一定 subjective， 不一定 isometric。OK， 就是你 you go and compute this reduce Mayer-Vietoris. Does it make sense? Okay, so the idea of reduce is we want to remove the H0 term if your space is connected. Okay, if your space is connected, then it's reduced. So for example, okay, so let's put a remark here. So if A intersect B is path connected, okay, then reduce zero homology of A intersect B should be 0. Okay, so this will implies that H1X will isomorphic to H1A plus H1B over image of this previous map. Okay. Yeah. Okay. So then this is the like your Van Kempen stuff. What did you do in your Van Kempen? You take a free group generated by the pi one of your open set and then quotient by the inclusion map. This is the inclusion map. So this is a abelianized version of Van Kempen. Because Van Kempen you put pi one here, right? Now you put H1. Yes, question. This is a short exact sequence of chain complex. So every level will form a short exact sequence here. So why is it 0 here? Because this map is injective. Yeah. So A intersect B can map into A and also can map to B at the same time. Yeah. So you can sit inside A. So the map looks like this. So you can sit inside A. You also can sit inside B. Is it Van Kempen? Van Kempen, what Van Kempen do? You need to look at the loop that sit inside A and sit inside B. And multiply one with the inverse. This map is injective. It's okay. So there's a short exact sequence. And then surjective, that thing is surjective. You just split something in A and something in B too. If it's in A, you go to A. Oh, so what's this map? Okay, do you know what this map is? So let's say AB is here. So you just send it to A plus B. Okay, so this map is surjective. Because we already said that all this chain is coming from A plus B, so you can split the from A to A and then split from B to B. So it's surjective. So what this term means? Let's see. So I think, yeah, I think we
chain and chains are some.
Yeah, let me see. So this is basically the this is so this is sum of chain in A and chain in B. Let's see. Yeah, sum of chain.
Some of it
就是就是如果你有 simplex in A simplex in B 就把它加在一起就好。加，真的加，就加了。Because chain you can add, right? It's an abelian group, right?
你加这个 group 里的 element 跟你加别的
它有不变形。
什么意思？
再加direct sum
没有，就是 abelian group 的加。Direct sum is like R2 这样嘛，你就放在旁边嘛。
chain 上面的东西别的 group
对啊，abelian group，所以我就加
里面的 element
abelian group 里面的 element，怎么不可以做
Abelian
加法？什么意思？这个 CN 里面的 element 是一个 chain，你 abelian group 里面的 element 做加法跟 chain 做加法什么差别？里面的 element 是 chain，对吧 element 做加法什么问题啊？
我有听过 chain 的想法，
就是因为我们说它是一个 abelian group，或者 Z module 有加法，这种 additive。什么问题？还有问题吗？问题
这边 A 应该有
啊、right，说这个是很好的问题。Let's see 啊，
如果你能把所有 A 写成 A，
等一下啊，这个是很好的问题，因为这个是之前我们好像没有花时间在里面的东西，但是我可以告诉你去哪里读。东西在哪里来着？这个 A plus B 的故事好像是发生在 cellular 的时候就出现了，是在这故事在哪里啊？在这边，在这个 accession 的故事的时候就出现了这个 notation。你要回去看一下这边，这里就出现了。OK，so actually Mayer-Vietoris is a generalization of accession。其实你回去看这一边，这个 A 加 B 跟那个 union B 的 x 本身怎么回事？对，我这边也有 like，你看这个 CNU，CNU 应该是刚才那个加 A 加 B 的东西，这 notation 有点不一样，但是还是 sum of chain。OK，这个 U 你可以想成是刚才那个 A 加 B 啊，没有记错了。对，OK，A 加 B，这个是 A 加 B，U 是 A 加 B。来说这个 U 是 collection of sum of chain in UI，sum of chain in A，就是你的 chain 的 image 是活在 A 跟 B，A 或 B。OK，所以你要回去看这个 accession 的东西，因为这个 Mayer-Vietoris 其实是跟 accession 的东西。OK，说不要讲这个 proof，then 我们就去它的 我们就去它的 examples。OK，so yeah，我们就去 example。其实technically there are three types of case you can apply here. Okay，so one is x that can be written as interior of A union interior of B, and then second case is A equals to A union B such that U deformation retract A and V deformation retract B, and then U intersect V can deformation retract to A intersect. Okay, so the idea is you have A, you have B, right? Then this cover of A and cover of B should also deformation retract to the intersection. Okay. Yeah. Okay, and then the third case is CW complex. Okay, so if you decompose into subcomplexes, you also have this kind of property. Okay, there's some retraction from the neighborhood of A and neighborhood of B. Okay, but to talk about CW complex, you need to define a topology there, so you need to define what's neighborhood there. Okay, but the story is you can decompose. The end story is if you can decompose your space nicely, okay, nicely in some way, then you can do this. Okay, so let's give some examples. So after this example, maybe you can take a break. So first example is we take X to be Sn, okay, and then we can take the southern hemisphere, and then northern hemisphere and southern hemisphere. Okay, such that A intersect B should be just Sn minus 1. Okay, so what is hi of A, hi of B is 0, right? Because they are contractible. So in the end, from the long exact sequence, what you left with, you only left with the intersection term, which is Xn minus 1, which is isomorphic to the hi minus 1 from the connecting homomorphism. Okay, you only get this isomorphism here. Okay. You 错吗? Did I write down the wrong indexes? Huh? Did I write the wrong indexes? Index 有错吗? I think 没有 right? Because 看一下那个
是 SN
对
是 SN 吧？
对，我没有 the ballet. Did I the ballet? So okay. So how about let's write down the long exact sequence first. So hi of A intersect B goes to hi of A plus hi of B, and then you go back to your original space, right? And then you connect with your connecting homomorphism. Okay, so because we say that this two term is 0, so what you're gonna get is hi of x. So 确实有错. So this is hi of xn go to hi of I minus 1a. This one makes sense because we know that last time we proved by induction, right? Hn of xn is equal to hn minus 1 of xn. This one is z. So this is another way to get the reduced homology of xn using Mayer-Vietoris sequence. Okay, last time what did we use? What did we use last time? We use 什么上次? I think we reduce 去那个零的 case 嘛。
哦，对，
那个什么情况啊？讲做出来那个？哦，那个只是普通的 long exact sequence 吧。我们 consider 一个 pair consider 一个 pair， 还记得吗？我们 consider 一个 pair 是吗？
就是 by induction。
啊，by induction 啊，对，但是是从哪里来的？也是 pairs。
好像也是用了那个
Yeah, long exists sequence. Where's the long exists sequence come from? This is my question. Coming from pairs, right? What pair we consider? Suspension? 吗？忘记了。Wait, let's quickly check it.
奇奇怪怪的。
诶，怎么我找不到嘞？哦，要 exact 过后才会有。Yeah, right. Okay, so we pair of dn and Sn minus 1. Okay, so pair of dn and Sn. So the contractible space that we consider is here is dn, no? But for the Mayer-Vietoris, we consider two contractible space, which is dn minus 1 plus dn minus 1. Okay. Okay. Right. So you have two ways at least to compute this guy already. Okay, next. Next, let's look at annulus. Okay, look at annulus like this. Annulus. So how do we form a AB here? So first we're gonna take this part A. Then we take the other part B. Okay. Okay, makes sense so far? Okay. Although I draw outside here, you should think it as a subset, because I just want to make it easier to trace. Okay. Okay. So it's actually a subset. Okay. And then, so what we're gonna do here? So we want to look at the Mayer-Vietoris sequence. So let's write down the sequence. We like to play with the reduced one because we don't want to keep our H0 non-trivial. Okay, so if you look at this Mayer-Vietoris term here, what did you see actually? What did you see? Okay, there's a lot of zero term here. Can you recognize what are zero inside these terms? So these are the first few in the list. We don't go to the higher case. Which term are zero here? Can you recognize? A and B are just these, right? Okay, so this is zero, this is zero, and then A intercept B is what? Two circle, two these, right? So also zero. So this one also zero. A lot of things are zero actually. So only thing we left with is this delta one here. Okay, so how do we figure out this delta one? Isomorphism good. So what's the map? You know what's the map? Can you figure out what's that map is? So in particular, what is H0 of A intercept B? So A intercept B is where? It's just these two parts, right? Okay. So there's a point that generates this homology here. So let's call it is P, and then let's call this Q. Okay. But reduce means what? If H0 not reduced version, should be Z plus Z, right? Because there are two parts connected. But after reduce it becomes 1. Okay, because one of the Z you take it. Doesn't make sense. Okay. So then what's the map here actually? What's the map here is going on? So what's the cycle, for example? What's the cycle in H1? Can you recognize what is the cycle here? What's the loop here in particular? Okay, so for example, if I call this path that connect PQ is A, and then path connect PQ in B is called B, then this path is actually, this loop is actually a path. This is a cycle. Okay, why is it a cycle? Because if you evaluate this connecting homomorphism here, what do you get? What do you get? What am I writing here? So the partial one of AB, let me see. So partial one. So partial one. Yeah. Partial one of A hor. Let me see. Do we have an order here? Actually, we have an order here. So does it matter or not if we pick a different order? I think it matters. So I think we need to pick orders on our part. So one is so a bit confusing. So let me remove this. Okay. So one of it for A, I pick from P to Q. Okay, and then for the other one, pick from Q to P. Okay. Okay. But if you trace through this connecting homomorphism, I think you need to trace through it. Okay, you need to trace through it such that you will get this equals to pi 1 of A, sorry, partial 1 of A, which is equals to minus partial 1 of B, which is equals to Q minus P. Okay, so actually this is generated by Q minus P. I think you need to trace through what is this map here using the connecting homomorphism. Do you still remember the formula? I think I here and P partial here and then P inverse, something like that. Yeah, you need to trace through this map here to compute this. Okay. Maybe I can help you to trace later, but not now. Okay. Yeah. Okay, so this is the generator in the H0 theta. So this will become generator in H1 theta. And can you see the loop inside here? A plus B. Okay, this is a loop. All right. You want to continue or you want to take a break? Break. Okay. So let's break until 10:16. Yes, I think this this pi 1, because pi 1 of A plus B has to be 0, right? It's in a cycle. So then I think because of that, because this is pi 1 the homomorphism, so it's split into this. And 怎么我这样子写哈？感觉我是白痴了。My stupid。怎么我这样写？我知道这个东西是送去领了。And then obviously 我懂这个是等于这个 ，but then 我在做什么？感觉这个 pi one 呢，Yeah, I guess 我觉得要算一下这个 pi one，从后面的，看一下这个，怎么只有 action 在 pi one 上面，在 A 上面，不能掉它。我觉得我要补一下这个东西。
那个 rectangle 一样吧？
什么呢？
看来 A 的太 B 的没有差，那知道了还自己你不要partial one A 加变 partial one A 再 partial one A。
没有，I think 我现在 confuse 的点应该是这个吧。 这个派 one of A 加 B 怎么只变到派 one A 罢了？肯定这是我 confuse 的点吧。这个，I think 我们要知道它这个派 one 是什么才可以做吧。有人能够 work 出来这个派 one 是吗？
就完了。
partial one，sorry， partial one。说 P inverse 嘛，对不对？P inverse I guess is just 就是放个 A B 在这里，and then 给它送下去，送去 del E A 跟 del E E，and then 什么东西要 include 进来？I think 我要 check 一下这个 Pi one 的东西，这个 partial one。咦，没手机，就是在 component 里面。I think 是 P 减 Q 跟 P 减 Q。呀，对啊，我对啊，对啊，good，非常好，我懂了。I mean like 讲这个东西哎，so I think you really need to trace it back. Okay, you need to really trace it back, and then because you use this I delta P inverse, right? So what's the P inverse of A plus B 啊？这个有点 label 错误啊，我只是记位置吧。Supposedly you should work with C1, 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 C0, C0, C0，还记得吗？那个图是你要一辈子记住了，for 那个 snake 的，就是 like C1, C1, C0, C0，就是这个东西将会来，你一定要记住这个楼梯 connecting homomorphism，还记得吗？就是这个 P，这个 delta，这个 I。OK，这个是 define 那个connecting homomorphism 的图片来的。OK，so 你看我这边有 A 加 B 嘛，记住这个位置啊 ，A 加 B，然后 pre-image 是什么？就是 A 跟 B 咯，因为你 A B 送过去是 A 加 B，and then A B 送下来是什么呢？就是 partial，就是 boundary map on 它咯，and then the claim is 因为这个东西是在这条线的 kernel 里面，所以它是它的 image。但是它的 image 谁送去它的 boundary，谁是它的 boundary？一个是 P 减 Q，一个是 Q 减 P。因为这个 boundary map 很正常，这个 boundary map 就是你们一开始学的 boundary one of 的线，所以就是头减回 ，OK 吗？就是头跟头减回，所以头减回头减回，所以它 include 过后，actually 就是这个 term 来的，所以 P boundary one 这个东西就是这个或者减这个。Make sense 吗？Make sense？
Yeah.
Yeah. 我想想啊，Yeah.
写8,000 A 等于
Yeah.
8,000 B 是，
partial one A 哪一个？
如果你
这个加，这个不是加，这个是这个 term 来的，这个是一个 IA 跟一个 IB 来的。
对啊，我
那个
没有讲
啊哈，
partial one 减 partial one b 嘛，
这个啊
那个蓝色的。
哦，这个啊，呀，对，这个是因为这个 inclusion map 的问题。
then
嗯
partial one a 是
嗯
u 的 chain，partial one 减 partial one b 是 v 的 chain，then 他们的 chain
呀，
一定要在 u 你的在 b 里面。那你选其中一个来做它的。
对，选其中一个的问题是这一点，这里是选其中一个的意思，懂什么意思吗？为什么选其中一个就好了？是因为这个 part 这边，因为它一个就可以做出两个东西来，然后你假如做出第二个，其实是这个 inclusion 有一个 negative 在里面 ，OK 吗？明白吗？因为是这个 connecting map 的特性，让到你这个 partial map 只要看一个就好。为什么？因为你的 pre-image 是分成两个东西，然后这两个东西是 come from 一个东西，然后你只要 relate 这一个跟这一个的 partial， 就是拿另外一个的 negative， 因为一个的头是 p， 一个头是 q。这一个 partial 比较 direct， 这一个值的 partial 是比较 direct， 这个就是头减回本。但是 connecting homomorphism 不一样 ，connecting homomorphism 你要经过这个 pre-image 过后 boundary 在过后，它属于被 include 进去。这是那个 connecting homomorphism 的跟 boundary map 不一样的地方，但是它是 depend on 这个 boundary map， 因为你的 direct sum come from 一个东西吧，其实就是这个 p 减 q， 所以你看它被送去 p 减 q 或者 q 减 q 减 p， 所以其实是 q 减 p 啊，所以这个是 q 减 p 啊，什么？对，他们从一个地方来的，所以你要从这边 a 加 b 送去这个 q 减 p，OK 吗？这个 OK， 我知道 confusion 在哪里了，我知道 confusion 在哪里了。所以这个 connecting homomorphism 其实不应该叫它 pi one。谁我要把谁的名字换掉？你觉得？
delta
把 connecting homomorphism 换掉，把这个换掉。我知道 confusion 在哪里了。这个是 del e， 就是 connecting homomorphism。然后这个 partial e 是这一个直线的那个 boundary 的。OK， 这样 OK 吗？这样 OK 吗？OK。Yeah, question. What if I start from P 什么意思 ？P minus Q， 你是说转方向啊？可以啊，可以转方向啊。I think 你转方向，另外一个也要转吧，应该。Yeah， 可以啊，没有问题啊。你就 change basis 罢了咯。你只是 change from Q 减 P 去到 P 减 Q 吧。你 change basis。OK， 有问题吗？还有其他问题吗？OK， 没有问题的话 ，again，let's play around with torus. Remember that last time we used addition to discuss about the homomorphism of a torus, right? So now we will use Mayer-Vietoris. Actually, um, very similar to addition for torus case. So what we do is we take this of radius 2e to epsilon here, and then let b be the complement of the disk of radius epsilon. So meaning instead of you take this epsilon, you take the complement. Okay, can see that these two things constitute your T. So meaning T is the union of interior of A plus the interior of B. Okay. Addition last time we just take one away, right? But now we need to consider a complement of a smaller disk. Okay, so that I can fill the whole thing. So meaning what then? Meaning I take away a small disk of epsilon, and then we take a 2 epsilon disk to cover that whole. So these two things build up our torus. Okay, in this case here, A intercept B is S1, okay, but A is contractible, and then B is what? B, I think you should remember from exam, right? Is S1 wedge, X1. Okay. Deformation retract to the one skeleton. So what's the Mayer-Vietoris here? So you can start with H2 because higher one is irrelevant. You can write down the higher one and then convince yourself that they are irrelevant. Okay, so you get this. Right. Right. I think, is it enough? Enough to see what's here? You see here. So, intercept B. Okay, so I think there's a very crucial problem here is what's this map? What's this map here? What's this map? You know what this map is? What's this map? How x1 sit inside one of the x1 and sit inside on the other s1. What's these two s1 here? So what are these three s1? Right. So I think we need to give names first. Okay, give these names first. Okay. So one of it should be generated by A, right? And then the other is generated by B, right? Okay. And then this one is the circle, I mean the intersection circle here. Okay. So your intersection circle deformation retract to S1, which S1, right? But how does it deformation retract to them? A, B, A inverse, B inverse. So your deformation retract to A inverse, B inverse. So what do you get? Actually, you get the identity. So what does it mean here? Actually, you are a zero map. Okay, so actually it's a zero map. Okay, so yeah, last time 上个礼拜你没有来，对不对？对，我们提到说这个 map 其实是 counting 罢了。Okay, on the logical space level, right? You would think that I need A first, B first, and then B A inverse and then B inverse. But when we move to homology, we kind of make this into like 1 plus 1 minus 1 plus 1 like that. Okay, so we actually just count. 你粘了几次，我管你怎么粘的，你粘了几次吧。Okay, it turns out that it's already enough to tell stuff about the space. You understand? Enough to differentiate space at least. So the ultimate goal is for mathematician is can we recover the space using homology? Okay, obviously we need something else, but they are trying to work toward this effort. Yeah, we try to use homology to recover space or build space. Okay, for now is we reduce from pi1 to just counting. How many times I look around A? A inverse with orientation. Okay, got A inverse. Okay, yeah. Huh? What? 不是 zero， 是那个 circle。这样子。Yeah, sorry, be confused.
后面那个 map 是 zero。
Yeah, 那个 map 是 zero， 因为 you map to A, you map to A inverse again, then you map to B, map to B inverse again. Okay, so it's the identity inside here. This is a module way of writing, if you isomorphic to Z, they are zero. Because this is A to the 0, and this is B to the 0. Okay, so far so good. Happy? Happy or not? Okay, so if this is 0, then this means these two are isomorphic, and then these two are isomorphic. This is what you want to get. So this is equal to Z plus Z. OK， 可以吗？我可以 skip 啊，我可以跳啊。下一个 example 是 RP， 下一个 example 是 RP2，那你们自己去看可以吗？ 还有一个 climb model 也让你去看，可以吗？很好玩，OK 吗？说法有信心吗？可以吗？可以啊，呀，一样的方法，OK，but but I think RP2 还好，but climb border 比较好玩，climb border is split into two Mobius band，所以你会看到 homology of two Mobius band 出现，Mobius band，yeah，Mobius band，然后 actually I put 2个方法去算 climb border，除了你可以把它分成2个 Mobius band，你也可以分成诶，也可以像这个情况，拿掉一个 dis，然后它也是这个情况，只是它的 blueing 是不一样的。Mobius band 的做法就是上次我 show 给你的那个Mobius band 的切法，还记得吗？不知道你知道，还记得吗？对，Mobius band 的切法是这样子的，这样子呀，说你把对它多的切成2个 Mobius band，就是你从哪里切开？从从另外一个来的呢把它切开，OK，把它切开。然后另外一个解法就是你可以用刚才那个 torus 的方法，拿掉一个 dis，拿的另外一个 circle，看不掉那个 dis。这2个方法都是 Mayer-Vietoris。你可以这样子做，因为它是 CW complex，所以sub complex is always a good pair，所以你可以apply Mayer-Vietoris。OK，这2个都很好玩，你们可以去玩玩看。OK，so then now，哎，这个礼拜是 Adrian 做 notes 吗？你是最后一个人了。Yeah，so Homology 我不知道谁要不要做，你要做的话就可以给你高一点分。
是啊，
真的真的，多做工的人当然是多的工钱嘛，对不对？就这样讲。OK，but anyway，差不多我的 Homology 有增大，所以它整部说现在有1300面，然后我们现在是 stop 在800多页的 Homology，所以 Homology 差不多有整个 Seng 的东西在里面。那个长度 wise，but content wise is repeating what we did for Homology. So how you should think of Homology is we repeat everything for Homology, and then we have extra stuff. We have extra structure in Homology. 全部 Homology 能做的是 Homology 都可以做 ，and then 我们再有。Yeah, so the why we can change arrow is because there's something going on. 我到时会跟你们讲一点点啦，等你们就会有一个概念，说怎么 change arrow 就可以用。OK，
我一直为什么去 narrow 会大？
等下我们就会讨论，等下我们会讨论。OK，好，so 如果谁愿意接下个礼拜还有后个礼拜的工的话，就我们可以给多你一点补偿，分数上的补偿。OK，
请说。
现在经济有点拮据，sorry，投资不上，没有，开玩笑。OK，来，so OK we'll continue. OK，then I think pretty much we finished Mayer-Vietoris already. Yeah, we finished already. So Mayer-Vietoris is the technical part that you need to know is you know how to split out your space or not? Okay, after you split it out, do you know about the homology of the space that you split up? Okay, 明白吗？OK，说第一个你要猜的方法呢，你是猜成库一的东西，你才可以用这个 Mayer-Vietoris。I think 考试一定会出，OK 有出，应该我有 hint 给你看是怎么去猜他们啊。Then the point here is 什么意思
考本身会的。
？Yeah, something like that 啦。但是就是呀，我会告诉你一些 homology，你要记得一下就可以了，应该。一些基本的 space 的 homology 你要懂一下，我会告诉你。我已经会告诉你怎么猜。基本就是 lecture note 里面写过。Yeah, so I think for 这个考试的话， focus on lecture 应该就应该 OK。好，到时再跟你讲什么地方你要注意什么。Okay, next we want to do homology with a different coefficient. So all these while we just care about z. Okay, how about we change z? Okay, for example, 我们有 cx on z, right? So which is like equals to z on some either singular simplex or simplex or cells or what, right? Or cells or simplexes, right? So why not we change coefficient? 你觉得有问题吗？ Like we change to other commutative ring. So let's say R here. 也是一个 R module, right? Okay. Maybe I just show you one example, then you will click. Okay, you will click. So let's see which example I want to show you. So 全部 homology 会 work cellular including cellular boundary map 也会 work. Okay. You prove, 但是不要讨论。Okay, let me show you one examples. I think examples of RPN is very nice to talk about this. So I still remember RPN. So what's that? 那个 cellular chain. 还记得 cellular chain 长怎样吗？RPN. How many cell? How many N cell? Every level you will have one N cell. Okay, so maybe you can put R here. Up to level 几啊 ？Up to level 几？比如说 RP2，RP1 有什么 cell？Zero cell and then one cell. Okay, so up to N, I guess so up to N here. So level N, level 0. Okay, and then what's the boundary multiplication map 还记得吗？multiplication map 长怎样 ？boundary map 长怎样？还记得吧？还这样讲 deduce 嘛？这个很重要啊，这个会考啊！我跟你讲，这个会考，这个你一定要会，你闭着眼睛都要会，你睡觉也要会。所以上次I think 只是3个礼拜吧。So 我看一下这个，我们讲 deduce 它的 boundary map， 有人还记得吗？呀，这个我们用 degree of the boundary map。OK， 我们粘下去了过后，然后再 collapse 它的 complement， 然后还记得这张图吗？记得这张图吗 ？One side 我们用 identity 粘 ，the other side 我们用 antipode 来粘。看这张图啊 ，one side 我们是 identity，the other side 是 antipode。OK，so degree 是 2。OK，so degree 是 2。怎么会有20呢？2020 because depend the degree of the antipode is depend on the dimension 里面 ，OK，so depend on 你看哪一个 cell，OK，either 这个减一是1，either 这个减一是减1，OK，so that's why you have this alternating， 这个一定要会啊，这个一定要会啊，我要你 challenge 你自己去解释给一个 undergrad， first year。哎，我在想哦，我们要不要 start 一个 research group 啊？让那个 first year 就开始进来听，因为这个是 AI 他们做的事情，他们 second year 就去 join 医生老师的 research group， 他们就开始读 paper 啊，AI 题，好像 work 得蛮好，我再去研究一下怎么实现这个事情啊，没有经费。我们再去研究一下怎么实行这个事情。这样的话，我们也可以让那些学生有点动力，他不天天看到 iPhone 掉到就想吐掉，对不对？
一定没有动。
对，我知道他们没有动力，因为他们没有这些东西去 push 他们，他们天天只看课本吧。我觉得我也没有动力，我只看课本。我要去跟那些人一起真正的玩数学，一起玩数学啊。
看不懂吗？你电脑
所以我们就要有一些动力可能让他可以发 paper 还是什么之类的，他就I don't know 啦，but anyway，so 研究一下，想一想看呢，你们想想看，哎，还有其实你们做 SEM 可以重复做我们上个 SEM 做的事情，这次你们自己去做，因为你们都读过了嘛，对不对？那怎样你们可以 online 嘛，对不对？呀，可以像上个 SEM 这样学一模一样的，但你们现在比较贵了
我要
可以因为你是新的人你怕么？新人没有听过，就算听过的也不记得对不对？
待会儿去打给
你们可以考虑一下而且你们现在比较贵了讲了也比较好嘛，OK，but anyway，but 记住这个 cellular chain 02020202，so if I come back here right，我在哪里来着？OK，so here is 零 start from here 零 start from here，020202，OK，so it depends OK，so just now what we had was hash nk of r pn of r is isomorphic to r 0 k for 零 for k 等于零跟 n 是 odd and then 0 otherwise because 什么呢？Because 2 is effective. But there's one exception. What if I replace this z by z mod 2? What does it mean? The image become 0. The 整条线 become 0. 整条线 become 0 means what? They are more non-zero homology 更多之前只有在零跟 n 会出现吧？现在是每一个都是怎么读？You understand or not? So if I change this to z mod 2 then you will just get z mod 2 all the way from 0 to n. 更多 homology group 跑出来。There are more non-trivial homology group appear. 为什么是更多？因为你的 chain 变 zero chain 了。What's the kernel? What's the image? 还记得上次讲过吗？如果你 if you have a chain complex with trivial maps, the chain groups are just the homology group because the kernel is everything, image is nothing. So you take back the origin. Can see 更多东西跑出来如果你放 coefficient 的话 ，OK。
切到多少？
那你讲怎么切因为 kernel 也是切image 也是切所以你要哪一种切 ？Yeah，but anyway 就是换 coefficient 的话，可能会看到不同的东西。或者说 sometimes homology with Zm coefficient right tells us that f is not homotopy to a constant map. Yeah，因为有时候它就算不是 constant map， 它也是拿到0吧。上次我们不是讲有 acyclic 的 complex 吗？它的 homology 是0，但是它 map 不是但是它 map 是，如果你还记得吧？还记得吗？但是我们有一个 acyclic 的 complex， 它的 homology 全部是0。但是它 map 是 non-trivial。OK，yeah。OK，so far happy？ 来，对，会影响嘛，对不对？因为你的 boundary map 的 image 是2乘什么东西嘛，它是2乘什么东西 ，mod 2是什么？你知道吗？所以那个东西变0，所以你全部东西都送去0，所以变成 zero map。OK，还有问题吗？I think 这个是 main point of 这是 coefficient Other than that， 什么 universal property 我们没有 discuss 在这边。会有 universal property 可能 restriction 还是extension 什么来的。差不多如果你们读完这一门课你们应该差不多可以看得懂我的 paper， 差不多到60%。我的 paper， 对 ，OK，so far， 可以吗？好，这样的话我们就要 wrap up homology wrap up 就是包起来收掉，打包带走。Okay, so now we will view what we have learned in a categorical viewpoint. So really, this is where category theory starts, actually. I mean, there's a lot of notion of category actually generalized from algebraic topology. Okay, so first is we will discuss reduced homology case first. Okay, so for reduced homology, right, you should remember that if we have a map, okay, f from x to y, okay, continuous map, right, and then you will induce a map on short exact sequence of chain complexes, and then we got the map between long and the sequence. Okay, so there's a map on the reduced homology case. And then there will be a functoriality here. Okay, if you induce F, G is F, induce G, induce composed with G induce. And identity induce is identity. Satisfy these three property here. So what's this three property? If these two maps are homotopy equivalent, then their induced map on homology is the same, the chain map. And then there's a long exact sequence. One continuous map can induce a long exact sequence. And then the other thing is maybe perhaps it's special is converged product. Okay, actually this turns out to be one of the axiom you need. Although last time we treat it like a very easy consequence, but actually it's one of the important thing we need to record it. Okay, so if you have these three property, then this is a reduced homology already. Yeah, no short exact sequence appearing. If you look at this definition, 没有 short exact sequence 的，它就是一个sequence of abelian group 就好了，没有 short exact sequence。OK， pass by 那个 short exact sequence。OK， 直接去something that has a homology structure。就是之前的 construction 是 we have a topological space, right? And then we have short exact sequence for topological space。什么？对 chain complex。哦 right， 等一下，给我反一下。对，讲错，给我想想。哦，我要想的就是 chain complex，thank you，chain complex，chain complex，thank you，chain complex，不是 long exact sequence，等下会去到 long exact sequence，还没有到。到了吗？Yeah， 到了。OK，so actually this long exact sequence here，OK， 我讲漏了。So this long exact sequence here actually is looking at a pair， 是一个 pair。Yeah. So it's a pair of X and A. Yeah. So okay. So again, so reduced homology theory is you have a continuous map between topological space, and then okay, sorry. So so if we have a reduced homology theory, what we had is we attach a CW complex, a sequence of abelian group. That's it. Okay. Then have to satisfy some property is that if there's a function between CW complex, then there's a function between these abelian group. Happy? Okay. And then three axiom, actually five of them because you also need to have the induced property here. Okay. Induced property plus this axiom, then will make out the reduced homology. So first is if two maps are homotopy equivalent, then F induced and G induced is the same. And if you have a group pairs, not necessarily group. Okay, it is group here because it's a CW complex. CW complex is always good if you got a pair. So you will get this long exact sequence for pairs. And then lastly is the direct sum of wedges. Wedge of homology of the wedge sum. So here, this is actually not true if it's not reduced. It is only true for reduce. So reduce 你会问发生在哪里 ？Actually 就是在这个第三条上面才有 reduce 的 property 在。OK， 因为 non-reduced one you won't get this. Non-reduced case you won't get this. You will get an extra stuff rather than this direct sum. OK so far. Yes， 问题。 就是special case，不是讲 special case，但是就是其中一个特征，其中一个 reduce homology theory 要给你的特征，或者 homology theory 要给你的特征，哎，其中一个特征，对不对 f u n d a m e n t a l i t y OK 吗？这个 theory 里面有这个 f u n d a m e n t a l i t y OK。你要讲我们讨论的 homology 是 special case of this 也可以，你要这样子想也可以。这个是一个很 general 的 reduce homology theory。
我用这样子的方式
Yeah
出来的人，
嗯，
转化成一个
就转换成什么？
就一定能把它写成一个 chain complex。
不一定啊，不知道，不一定嘛，对吗？不知道哦，你都没有经过 chain complex，你只是丢一大堆的 appealing 的 group 给他。就是不一定啊，我不知道，不一定啊，不一定嘛，你是对啊，因为你这个已经 pass by 了那个 chain complex 了，对吗？我只是直接从一个 topological space 我丢一大堆的 abelian group 给你，然后这些 abelian group 有这些条件。How we define topology in a topology? Yeah, sure. Okay. Yeah. Yeah, sure. Or rather shift, I guess. Okay. Yeah, so exercise is you can work out for non-reduced case. Okay, so how to get the unreduced case is you look at this pair here. Okay, you look at the pair. So just now we got the reduced for pair, right? But the pairs here, you consider the A to be empty, then you can try and work out the unreduced version. Okay. So reduced and unreduced homology are equivalent. Okay, in this case here. Equivalent is what sense? So in what sense? I guess in a functorial sense, I guess. Yeah. But anyway, you don't need to get so deep first, but they are somewhat equivalent. Okay, equivalent in the functor sense, I guess. Okay. Then you also have this very familiar property. Every reduced and non-reduced version will have this relation. Okay. Like what we had last time. Okay. And then what else? So every homology has a Mayer-Vietoris sequence. Okay. So you imagine that just now we define Mayer-Vietoris sequence for quite a few situations, right? But as long as you have this property exists, then you will have Mayer-Vietoris. So this theorem will say that as long as you have those axioms, then you can build Mayer-Vietoris already. So meaning you don't need to know about what's the actual topology happening, what's the chain，不用知道，不重要。OK， 重要是它有这些 axiom 在，你就可以 build 这个 Mayer-Vietoris。OK， 所以这就是学数学越学越远越好的一个原因，很多东西都给你丢掉了。Yeah. Yeah, sometimes when we want to work out the technicality, 确实是要回去懂一下以前的东西。Okay, next is categorical property of homology. So, 刚才是讲到什么哈？Categorical formal view. 这个是 axiom for reduced homology 吧？Okay, so 等一下我们会讨论周末我们会这样子 define 那个 homology 啊，现在开始讨论，这个是比较整体的来讲 ，OK， 从头讲到尾是什么东西？那比如说我刚才用的方格是，其实上次我们已经来不时不时我就丢一些这些字给你听，但是现在是从头到尾讲给你听啊 ，OK。Yeah, 就讲过一遍。So first of all, we have category. So repeat again. What is category? You need an object and morphism. So 你刚才看到的情况就是我有一个 CW complex, I give you a sequence of abelian group. So CW complex object. And then to a map on CW complex 我要告诉你 map between 那些 sequence of abelian group， 所以有两个东西要讨论，所以就是这个会 form 一个 category， 所以一个是 category of object， 一个是 category 里面有 object and morphism 里面的 map， 所以意思说比如说 set 是一个 category， you don't just care about finite set, but you care about map between finite set，对吗？比如说这个班，我如果把这个 classroom 想成 category of class，就是说我连你们的关系我要知道，哦，我知道这个是男女关系，哦，我知道这个是朋友关系，我要连这个都知道，你就觉得很给薄。但是就是因为我们要认识这个世界多一点，这个世界是有关系的，东西之间是有关系的。Not really, but we need philosophy here. OK， 明白吗？OK， 就算没有关系，我要知道它是没有关系的，它是自己跟自己有关系，明白？OK，so category 为什么会需要到，就是因为我们要 consider 东西之间的关系 and then satisfy some condition that I skip 了。OK，so there's a few category versus set with maps quiver。OK，quiver because got vertex and path 是 quiver 之间的关系vertex 之间的关系。Vector space linear transformation groups group homomorphism group between groups and homomorphism rings between rings got ring homomorphism between topological space there's a continuous map between them okay, so these whatever you learn up to now a lot of them are category。quiver 就是那个 map 是 path。If there's a path between them, there's a map between them. Okay. Other category, for example, group itself is a category. How do you think of group itself is a category? So you think of group as one object, and then all the composition as a morphism. This itself become a category. Obviously, you need to check the axiom, the associative identity. This axiom you need to check. Okay. So group itself is a one object category. So you take a group element here, and then all the other group element act as a morphism, like that. 很神奇啊。Okay, right. So 这个 G I think is G have to be viewed as G like that. 不是 group element 啊，是 G 啊。Yeah. 回去 G 自己，回去 G 自己，回去 G。Yeah. So because an element in G can define a map from G to G, right? Because you just multiply by that element, everything. And then partial order set 也是个category. And then this homotopy category is very interesting. Maybe you guys want to look at. Its topological space and morphism become homotopy classes of maps, not just continuous map. We want to put an equivalence relation on them. Okay, homotopy class. 什么 homotopy class of maps. So continuous map, we can put equivalence on it by homotopy. Last time we have we discussed when is two map are homotopy, right? Then if there's a homotopy between them. Okay, so we use that be our equivalence relation. This has a counterpart in the algebra, homological algebra sense. So there's a homotopy category of chain complex. Okay, did I introduce this? Yeah, I introduced this. Okay, homotopy category of chain complex. You see, so there's a category of chain complex, which is R module with chain map. Then there's a homotopy category here. So these just now we homotopy, we regard two maps to be homotopy if there's a homotopy between them. Now we regard two chain complex homotopy if there's a homotopy equivalence between them. And then we can go to the next one is the derived category. Okay, so this is what Hao Tian and some of my peer FIP are looking at. Okay, yeah, derived category. After homotopy category, you can go to this derived category. So you do some localization here actually. There is a localization of homotopy category. So there's something called quasi-isomorphism here. You don't understand, not important, but I want to tell you there's something exists like this. But for my FIP, I think it's important. Or if you want to do FIP with me, a master. Okay, and then between category, we have functional, but we don't call it function anymore. We call it functor. Why? Because function just have one input, one output. But here, functor is you need to input an object, output an object, and input a map, output and map. Okay, so this is called a functor. Okay, not just inputting object, outputting object. You also need to input a function, output a function. This is what homology do just now. Homology, you input a chain complex, output a sequence of abelian group, input a continuous map, output a map chain map. So homology is actually a functor between two categories. One category is category of CW complex. The other category is category of chain complex. And chain complex is a category. Okay, because the object is chain complexes of R module, and then between those chain complexes, there's a chain map. Okay. Yeah. And then there are a few things you can view as a functor. So for example, forgetful functor. Okay, don't want to talk about this. Dual vector space functor. You learned ALA before. Dual vector space functor is a functor because I give you a vector space, you give me a dual. And then if you give me a map between vector space, I also have a map induced on the dual vector space. Actually, this idea is we're gonna use in cohomology later. Okay, cohomology actually uses a lot of ALA idea. Okay, we look at the dual space, home from the vector space or the module to some scalar field. And then singular chain complex is a functor because reduce homology, homology theory. Algebraic homology is a functor. 什么差别啊？什么是 algebraic homology？什么差别的两个？哦、so singular chain complex is the singular chain. Algebraic homology, I think, is the general homology group. And then composite of the two functor is again a functor because like the so simplicial, right? So singular is like from simplicial to wait, 我想一下有错吗？ singular. Oh, okay. So 3 is just giving out the chain complex. 4 is go from the chain complex to homology. So this composite is again a functor. Okay or not? Correct or not? You have X, and then you give out the chain 0 cell, 1 cell, 2 cell, n cell, and then after that you compute the homology. Okay, so these two layers here, each of them are functor, and then compose together still a functor. Compose together become a homology theory, right? Okay, from a topological space to a homology. Okay, and then you can think of LES is a functor. Okay, give you a pair, you output LES, because if you have a map between pairs, you also have a map between LES, not as that sequence. So this is a functor. LES actually is a functor. Okay, so operation. And then now we talk about equivalence between categories. Okay, should we talk about this? No need. Okay, stop here. So tomorrow we will continue with homology, and then we will start with motivation in calculus. Yes. Sorry? Oh, it's on Wednesday. Wednesday. Okay. So Wednesday we'll start with motivation in calculus. You can start and read first.